Okay. So now we now have a little bit more clarity about the rest of the semester. So I'll just kind of quickly go over this with you, and it's all on the class schedule, so we just keep updating the class schedule, okay? So starting next week, we will be talking about a couple important things from the GPU architecture point of view. So we'll talk about GPU as part of the PC architecture, essentially to go into some of the data movement aspect of things. And this is very important when we start to use GPU for data-intensive applications. And so that you can fully understand some of the intricacies of CUDA main copy and some of the related topics. And then we'll talk about task parallelism. And so far, we have been talking about data parallelism and kernel. But then CUDA has a very important feature where we can use streams to enable what we call the task level parallelism. We can have parallel kernels going on at the same time. We can overlap data transfer with kernel execution. So you are now going into the next level of sophistication in your parallel programming. And then we will talk about, hopefully, one lecture on the advanced, so the higher level CPU, GPU programming using OpenACC. And this is an industry trend to have the compiler to help you to finish up the parallel code. So you will be annotating your code with some directives, and then the compiler will synthesize the kernel and the memory copy and so on for you. And these are very good, very useful tools when people try to prototype, their parallel programs. And then we will give you a very high-level introduction of how you can program GPU clusters. So I will go over a very, very rudimentary introduction to MPI. But the most important part is for you to see how MPI and CUDA can interoperate, so that most of the supercomputers in the world today and most of the data-intensive clusters that companies use and so on are all GPU clusters now. So this gives you a kind of a quick introduction to how you can apply some of the techniques that you learn in this class into clusters. Okay, so you can begin to scale out to even bigger scale computation. And this is also one opportunity for us to show that once you learn all these concepts in 408, based on CUDA, it's extremely easy to generalize that to other programming interfaces. Okay, so that's the reason why we don't teach a whole slew of programming interfaces. And there's a CS course for that, which is fine. But our philosophy here is that we teach you one interface to the level where you will be able to pick up any new parallel programming interface very, very quickly. So this is an example to show you how you can generalize some of the CUDA skills to a different programming interface. Then we're going to have a final exam, not a final, exam 2 on April the 23rd. So this is Monday, okay? And the reason is we could not get a space big enough for all of you on Tuesday. So this April 23rd, and we're trying to set the exam time a little bit early. Most of the students told us last semester when we had an earlier second exam, people feel that it was better, but overall. So we will try to start the exam around 6 o'clock-ish, but we're still working on the details. So that's why the time is to be determined. But it's going to be 1002 ECE building, the Granger hall, so that everyone can be together. It's just a lot easier when it comes to logistics. And then we're going to announce the exact time soon. And after that, we're going to have one more lecture on a potentially new topic and course summary. And the new topic might be related to, might most likely related to the some of the optimization techniques for your final project. And then, so we'll do the course summary and evaluation. And then on May 1st, we're going to do the final project town hall. So this is the last meeting where, either me or Carl Pearson will work with all of you and, go over the kind of the final checklist of things that you should, pay special attention to before you handing your final project. Okay, so, so this is also preceding the milestone 4, where you need to have a minimum of 3 optimizations already in place and analyzed. Okay, and so right around 10:15 today, Carl Pearson will come here and do a CUDA profiler demo, and that's going to be a very useful demo for you to learn how you can analyze the result, the kind of the outcome of your optimization, and try to understand how to explain where the speed ups come from and so on. Okay, and then May 11th is going to be the last day of finals. Is also going to be the project due date. You're more than welcome to turn in your project anytime, before that. But we really don't want to extend any more of the final projects, because some of you are graduating and some of you are going to need the grades and so on. So extending the project would actually affect how we can finalize the grades. So we really would like you to make sure that you can turn in a good project, okay, by May the 11th. Many of you are graduating on that Saturday, right? So congratulations, and also make sure that you remember when you make billions of dollars, you'll come back and donate to the new ECE building. Okay, so any question about the rest of the semester? It should be relatively clear at this point, right? And we're going to continue to update our study guide. There are a couple of things that we would like to do, but as is, the study guide is already pretty good. So you should begin to look at the study guide and begin to prepare, for the second exam. Okay, and the study guide will help you to get a little bit deeper into some of the material beyond your MP. Okay, so that's something that is really worth the investment. And we also give you 2 exams with answers, right, from the previous semester. So this should give you a pretty good flavor about what you're going to see. Now, let's go and finish the sparse matrix and sparse method lecture. So this is let's do a very, very quick review of what the jagged diagonal sparse kernel is about. So remember, we already covered this one last time. We have these rows, and these rows of the sparse matrix, and these rows can vary, quite significantly in length. So, in the basic design, we have these row pointers, and we know where each row starts, so that all the threads can just come here, use the row pointer that corresponds to the thread ID, and get to the starting point of the row, and then every thread will just increment by 1 each time it does this matrix, the inner product step. So the advancement for each thread is going to be within consecutive locations. However, if you look at the access pattern for all the adjacent threads, they will be advancing side by side horizontally. But unfortunately, the location that each thread, all these threads access, will be actually quite a few locations away from each other. So we're still going to have memory coalescing problems. And so the JDS immediately solved the control flow or control divergence problem by sorting the rows, right? So now we have the rows sorted. And whenever we say we sort these rows, we're reordering the data as well as the column index. Okay? The data and the column index elements need to move together when we sort these rows. So now the rows are going to be ordered from the longest to the shortest, and that's why you almost have a kind of a diagonal matrix, but it's kind of jagged. Okay? So that's why this is called jagged diagonal sparse representation. When we resort these rows, we still need to make sure that the output element written by each thread is the original element that the thread should be using. So we actually, keep track of that information with the permutation matrix. So the permutation matrix will be used at the end of the inner product and write into the correct Y element. So this is the JDS, and then we showed a simple example where we have the original sparse matrix, and then we sort the rows so that the longest row will be on top, and then we go down, and the row with 0 element will be at the bottom. And then I showed you a quick comparison between CSR and JDS. So, the interesting fact is that over the years we learned that the sparse matrix, is one of the most confusing topics. And we see a lot of confusion when students take the exams and so on. So that's why we added all these kind of additional visual aids for you to have that intuition. And I still remember when I was a senior year, one of the EM wave professors, he told us that when you look at some of these formula and the equations and so on, when you look at these equations and then you see exactly the story that these equations are telling, exactly what each symbol is telling you in terms of the physical force, the fields and so on, that's when you know that you really understand the material. So this is the same thing. When you look at a piece of code, when you look at a piece of kernel, when you look at the variables, when you look at the constructs, you know exactly the story, okay? And these visual aids are the aids that help you to be able to tell that story, to be able to, to have that story with you when you read a piece of code or when you debug a piece of code, where you do the performance tuning of a piece of code. Without the intuition, you will be relying on too much on memory, and also you will most likely make mistakes without even being able to see it. Okay, so that's why the best engineers have to have the intuition, have to be able to look at a piece of fairly complicated code and see that story, see the intuition, and whenever there's a mistake in there, it will pop up right away when you have that intuition. So we have the CSR representation where we have the row pointers that will tell you, where the row starts, and then for each row we'll have the data and the index in the representation. And so when we sort, we will move the entire row together to different locations. So row 2 will come here, and then we would adjust the row pointers so that the row pointers would be adjusted to the beginning of the reordered rows. So all the threads will be able to go and pick up the reordered rows. So thread 0, instead of processing row 0, will now process the original row 2, right, which is the new row 0. But the inner product that it produces need to be written back into output element 2, right? So that's why the permutation row pointer gives you that, if the row index gives you that information. So you'll have exactly the right information when you need to write the result into your output. So these are the 4 important data structures. The data and the column index are exactly the same as before, and the row pointer is the row pointer that, with the same row pointer but with the values adjusted because of sorting, and then the permutation allows you to write into the correct output element. Now, we have seen a JDS kernel, and the JDS kernel is fairly straightforward as long as you understand what the representation is about. So every thread still comes in and calculate the row index, right? So that's just the consecutive and the coverage of all the rows in the reordered space. And then you will use the row start and a row end to pick up where your row starts and where the next thread's row starts. And so you're going to be incrementing your index between these two. So the element is the index. So your element will start with row start, and then you will end before the next starting point, and then you would do the inner product. So you will use element to access the data, and just like the CSR, you will use the column index selected by the element to access the X vector, right? Because the original column number gives you the X element index that you should be using. So, and then, so this is exactly the same as CSR, right? The only difference between a JDS kernel and CSR kernel is that permutation. Okay, so that's why you should expect that the rest of the code are pretty much identical. Okay, now, so at the end, this is where the big difference is. You use the JDS row perm selected by the row number to write into the correct output element, right? So then we're done. So the control divergence is nice because the threads will still execute a different number of iterations in the JDS kernel. We did not pad anything, right? So there still will be variation. However, because of sorting, the neighboring threads will likely tend to execute similar number of iterations, because they will be processing similar number lengths of rows. So that allows us to minimize, not necessarily eliminate, but minimize control flow divergence. And so this is a good quality. But the adjacent threads still access non-adjacent memory locations, and this is kind of where we left last time. And so if you look at the iterations, during the first iteration, the adjacent threads are accessing these non-adjacent elements because these are the beginning of the rows, right? For row major order, they will be elements apart from each other. So that's why, as you would expect, we would do a transposition. Okay, we will do a transposition of the matrix. So this allows us to have all the threads to be going from top to bottom in columns, right, in each column. But then, if you look at the first elements that every thread access, all the threads are now going to be accessing adjacent elements. Right? So that's why the memory coalescing works. So this transposition is going to also create some interesting problems, and that will make the code look quite different from the JDS, from the CSR format. So instead of being able to tell the beginning of the rows, now we actually need to know where the next original column begins. So essentially, after transposition, we still need to know the quote-unquote row pointers, right? But the rows are actually the original columns in the CSR. So we call it JDS column pointer. And this is really marking the beginning of the original original columns in the CSR format. And whenever you have these transpositions, it's actually very, very confusing because conceptually, you're accessing the original rows, but after the transposition, you're physically accessing the new columns, right? So, so that's why I always emphasize that we're talking about the beginning of the original columns of the JDS rather than the transposition when you look at these pointers. So intuitively, these things are still necessary because we need to know where the transpose rows begin. And then, so in every iteration, we're going to access, let every thread to access their column, and then they all come down to the next row, and then they use the thread index. They use the thread index to offset themselves from the beginning of this location and pick up their elements. Okay, so this is going to be reflected in the code. So, and then they're still going to be using the column index to access the vector, and they're still going to be using the permutation row index to access the final, to write into the final element. So let's take a look at the transposition. So the transposition intuitively is very simple. The original rows becomes the new columns, right? So then with the row major layout, we're going to have, this is the transposed matrix. So in the C layout, we're going to have 2, 3, 1, 4, 1, 1. So 2, 3, 1, 4, 1, 1, and 1. So this is the sequential representation after the transposition. So it is indeed different. Okay, it's indeed different in the physical representation. And also, the column index need to be transposed with the data. Okay, whenever you do anything to the data element, you need to do that for the for the column index as well. They have to go hand in hand with each other. And then we're going to have the JDS column pointers. So these are the markings of the original, sort of the original columns are now the beginning of each row in the transpose form. So that's why we have 0 that pointing to 2, which is the beginning location of this transpose row, and 3, location 3 here that points to the beginning of the next row, and location 6 that points to the beginning of the next row, right? So that gives us the transposed, the beginning of the transposed rows. And we call it a column pointer because they correspond to the original column, okay, of the CSR format. And now, after the transposition, we now have memory correlation. Because in each iteration, let's say iteration 0 here, we're going to have 3 threads, right? 3 threads. Each of the threads will be accessing their first element, right? And so these elements are in consecutive locations. And then we have the next iteration. They're accessing consecutive locations. And finally, only thread 0 will do 1 because that's the only thread that has 3 elements. The other threads all only have 2 or less. So as soon as each thread finishes all the elements in that transposed column, it will stop, right? It will exit that for loop, while loop. So here is a kernel that we're going to write for JDS transpose representation. So as you would expect, the row is still going to be the same calculation. So the row here corresponds to the non-transpose form. Okay, so conceptually, we're still talking about the original row of the CSR format, right? So that row, if the row is in the valid range that is less than the number of rows, then the thread needs to do something, right? And then so we do the inner product. So we say, okay, we're going to have dot equal to 0, and then we're going to have a section which is essentially the iteration index. Okay, the iteration index, and we're going to start with that iteration index as 0, and then we're going to this while loop. So every thread, okay, every thread is going to continue until the end of that column, right? until the end of the column. So how can we tell? There are two ways you can tell. So the way that I usually do it is this. So by looking at, so whenever I go into an iteration, the thread is going to see that, for the, you can access the column pointer. So let's say if I were going to do the iteration 0 and then iteration 1. Okay. At iteration 0, I have 1, 2, 3, 4, 5, 6, 7 elements. So when I subtract the next pointer, the current starting pointer from the next pointer, I'm going to get the difference, which is 7 here. So remember, all these elements are going to be all congregated at the beginning of the beginning of that representation. So thread 0, thread 1, thread 2, thread 4, they're all the threads in the low end of the thread index space will be processing these elements. And any thread with thread index greater than 7, greater than or equal to 7, 0, 1, 2, 3, 4, 5, 6, greater than or equal to 7 will not need to do anything. So if you subtract the next pointer value by this current value, you will get 7, and then you test whether your thread index is less than that 7. If you're less than that 7, you need to do your work. If it's greater than or equal to 7, you don't do anything. So that's why, if you look at the kernel, we take the next pointer, we take the current pointer, right? The current iteration pointer, we take the next iteration pointer, we do the subtraction and see if it's greater than your row number. The row number consists of the thread index, right? So if it is greater than your row number, then you're in. Okay, then you're in. So then you do the work. How do you do the work? You start from the beginning pointer of you start from the beginning point of your current row, right? Your current the iteration, and then your row pointer is going to give you the element that you want in that section, in that little section. So that's why we're going to use the pointer, the beginning location, plus the row number to fetch the data. We use the same thing to fetch the index, and then we use the index to get an X. Okay? So this is one of the key points of transposition. Essentially, after the transposition, the new row is really the old column, right? So essentially what we do is we go to the beginning of the row, and then every thread, active thread, is going to use its row pointer to offset from that beginning to pick up the element and the index. Yes?
Do you need a synchronization, like in the beginning of the row, to make sure the access to the data?
Okay. So the question is, do we need to have synchronization to make sure that they're all accessing the row together? Remember, memory coalescing is only relevant within the warp. And the warps are always synchronized. So that's why you don't need that synchronization. The only reason why you will want to use barrier synchronization at the beginning is because if someone else prepared the data and you want to make sure that everyone has completed the data preparation before you use that data. Yes? Yeah. Yes, yes. So this is a great question. So when you have remember this sec is really the number of steps that all the threads are taking, right? So, but because we have a while loop, and because the while loop, you exit the while loop as soon as the next pointer, the next pointer subtracted by the current pointer is greater than, is less than or equal to the row, right? So remember, the last one, the last fictitious section is going to be 7 here. So what does that mean? That means that all the rows, right, all the row numbers will be greater than or equal to that difference. So when you reach that point, all the threads are guaranteed to leave the while loop. So that's why the section will not increment beyond that point.
Well, isn't that because we had a row that had 0, that had no non-zero elements? So what if we never had a row?
Oh, even that. Let's say if all the rows have 4 numbers, right? But the fictitious row is still going to be at the same level, right? Because the fictitious row is going to have 0 element in there.
So we always add a fictitious.
Yeah. For this kind of algorithm, you have to have that fictitious row to end properly. That's exactly right. Right. That's the reason why we have to have that fictitious row. Okay. Very, very good. So this code, this piece of code looks a little bit strange, and but as soon as you start to have that picture about the purpose of the column pointer, right, which is really the same as a kind of a row pointer of the transpose, the matrix, and then you know that when you pick up elements, you're always going to, all the rows are going to pick their element from the beginning of the transpose array, and then each one of them will pick an element. Then this piece of code makes perfect sense. Okay? Any other questions about this? So this is how we wrote the code when we wrote the textbook and so on, and when David Kirk and I wrote the textbook. But the TAs didn't quite like it. So the TAs, when they did the MP, they actually set it up differently. So this turned out to be one of the confusions that we had in the previous semesters. And then finally I called on and said, wait a minute, guys, you guys set up the MP differently than what we did in the textbook. So but it's a valid approach. So I'm going to let them use that for the MP for this semester, but I need to explain to you how the MP is set up. Okay, it's slightly different. Everything else is the same with the previous one, but these are the names. The mat data is the data, correspond to the data element, so that's okay. So we call them data, and the MP calls it mat data, matrix data. And the column index array is called mat cols, okay, the matrix columns, which is fine. I would call them column index rather than columns, but that's okay. You know what, the TAs, sometimes they're little TAs. So that's fine. So matrix cols is the column index from the previous slide, and then the column pointer. Okay, the column pointer is called matrix column start, which is okay. This is actually not a bad name. So notice that they do not have the extra element. They didn't have the fictitious row here, right? So this is where the difference is going to be. And then the row indices, these are the permutation indices, so they are still the same. You would still use them. So this is called mat row perm, which is okay. So the real difference is a additional array called mat rows. So this is actually the length of the rows, of the original CSR rows, the length of the original CSR rows. And after the transposition, this is the length of the transpose columns. And NP is set up so that they give you this number. They give you this number so that you can you write a while loop for each thread. For each thread, you can use the row number for that thread to index into this thing, and this gives you the loop bound. Okay, this gives you the loop bound for accessing your column. And this makes the code simpler, right? But you need to give more data to the kernel. Now we created a new array, right? So the data transfer, at the cost of data transfer, you save some computation in the kernel, which is fine. You know what? It's a very legitimate trade-off, and you can even test which way is better. You can to potentially change the way the kernel is called so that and change your data transfer. Once you're done with the MP, you can play with it and then see which one is faster. Okay. I think that the original way will be slightly faster because we transfer less data. However, this makes the kernel code a lot easier to read, okay? Because now we essentially just have a for loop, and then every thread is going to be just using one of these elements to set up the for loop bound. Yes. Repeat that question. I thought you were asking about something else, but then I realized you were asking. Repeat the question.
So basically, you're doing COO.
So the question is, are we doing COO in a way that we can do this permutation? The answer is similar, because what we ended up doing was we used the permutation index, right? So when we do the permutation index, then we were able to reorder the rows. If we had strict COO, then we don't even need a permutation index because the permutation, the row index will be with every element. Then you can do total reordering. Here we're doing a partial COO, right? So that's why this additional permutation index is one element per row, and we do a low-cost COO, exactly. Mm-hmm. Yeah. Okay. Now the question is, can we actually begin to do a little bit of a partitioning, right? Now we can potentially say, hey, you know what? This particular part of the matrix is dense. So we can actually, organize the computation for this portion as a dense matrix computation, and that's exactly right. In fact, the best large-scale sparse matrix computation algorithms have localized dense matrix computation using pretty much, what you're saying. The data structure is a little bit complicated because now you need to represent these, sub-matrices with enough information that you can recover all the original row and index numbers, okay, which is fine. But then, when you can use dense matrix computation for a good part of that matrix multiplication, for example, you can get much better bandwidth out of it. So that's exactly the right way to think about it. And these things are quite complicated, but the concept is all rooted in this.
So you're doing like a per layer pushing down, like say,
Mm-hmm.
you're doing a layer pushing down like with
You will usually do some kind of block-oriented extraction, actually. So what you do is you say, I now represent the sparse matrix with multiple matrices. And then each matrix is a sub-matrix of the original one, and then you keep enough information to be able to recover the original locations. So you're not pushing down, but you're actually extracting multiple sub-matrices. Okay? Very good, very good. Okay, so now that now you're totally ready, okay, for MP7. So go ahead and finish it. With this these lectures, you should be able to finish the sparse matrix, MP, less than 2 hours. Okay, so do it this weekend. Don't wait until the last minute. Okay, and if you wait for the last minute, something will happen, and it will become much longer than 2 hours. This is the Professor Hu's law. Okay, whenever you wait until the last minute, anything that should take an hour or 2 hours will take much more. It's just the law of bad luck. Okay, the bad luck for waiting until the last minute. Okay, bad things only happen when you wait until the last minute. Okay, so this is Professor Hu's law, and you can remember me with that after you graduate. So I do want to point out a couple of things. So this is the last computation pattern that we're going to be teaching in 408. Okay, and so you wonder, is this the end of the road? Are there more things to learn? The answer is absolutely yes. So this is actually kind of where we start 508. And so sparse matrix is actually foundation for advanced algorithm techniques. One of the most important category of techniques enabled by sparse matrices is graphs. The graphs are often represented as sparse adjacency matrices. And they are used extensively in social network analytics, natural language processing, and so on. Okay, so the other important technique is binning techniques. They are often used sparse matrices for data compaction, and then they're used extensively in ray tracing, particle-based fluid dynamics methods, and games. Okay, so these are the techniques, part of the techniques that are covered in 508. Okay. So we're not teaching 508 this semester because we ended up teaching this course, but we will be offering 508 a year from this semester. Okay? A spring of 2019. So, any questions? Okay? If not, Carl Pearson is right there. So I promise you 10:15, and now it's exactly 10:15. So we will start Carl's demo, right now. So, Carl, do you need to have some kind of different? Do you need to switch to your own laptop? Yeah. Okay. So I'm going to make the switch. HDMI. Let's see if we can get both to work. Yeah, okay. Take this one. Cool. Where's the HDMI? Do you see that? Okay. Yeah. Perfect. Okay, take over. I'll keep you company.
Mm-hmm. Okay, is this good enough? Yeah, sounds good.
Yeah.
Okay, so I'm really up here to tell you about two things. One is that, is this pretty legible? Looks pretty good. So, it was better before. So one is that not for milestone 3, but for milestone 4. So this is a while from now. But and also for the final report, you're supposed to implement a certain number of optimizations for the project, or attempt a certain number of optimizations and discuss how well they work. And in past semesters, we kind of left this a little bit open-ended. But based on some feedback we got this year, we thought we'd try providing you a list of things that we sort of consider optimizations that you could pick from. So if you look at the milestone 4, or the final project rubric, you'll see that for, this is actually not up to date with the number of milestones, but you can see that you're going to have to do 6 optimizations. And so each of those optimizations, what you can do is you can pull one from this list to try. So some of them are, maybe optimizations really isn't the right word. They're more like approaches that you could take. So when you're doing the convolution, you could sort of do the straightforward shared memory convolution kernel, like we've discussed in this class. You can do the unrolling and matrix multiplication implementation. So, so that's this one, and then there's the shared memory one here. And then so there's this various list of things that we kind of consider as optimizations that we'd like you to attempt. And if some people really get involved in this project, and of course if you have some other stuff on this list that you don't want to attempt and you're worried that, or that you want to attempt that's not on this list and you're worried that maybe we won't see it as worthwhile in the same way you do, you can come and talk to someone on the course staff to sort of get that signed off on as being, a reasonable optimization. But we don't want to discourage you from doing something that's not on this list that you think is worth doing either. So this is kind of, if you're just like, oh, I'm just here in this class and I want to do some optimizations, then you can pull from the list. If you really want to try some good stuff, you can also come up with your own thing. And so what I want to point out is that when you attempt these optimizations and you write about them in the report, you're not really going to be graded on whether or not they worked or not, per se. You're going to be graded on whether you attempt it, how you describe it, why you thought it was worth trying, and your evaluation of its performance. Because there's sort of a separate component of the grade, the ranking, that captures how effectively you actually executed these optimizations, right? So we don't really want to like double reward you or double punish you for doing a good or bad job on these particular optimizations, if that makes sense. But if you go, oh, we thought we'd try this just because it was on the list, that's not good. You should be able to describe why these optimizations might impact the performance of the code. And so,
and also, we want to see some kind of profiling results
exactly
afterwards.
Exactly.
Even if it's not buying much performance as you would expect, at least you can show that you have measured and you have analyzed the data.
Right. And so if it doesn't show what you expect, it might be interesting for you to try to understand why that is, because you might be able to fix it, right? So that's kind of the second half of what I wanted to show here. And so I've mentioned this set of tools called NVProf and the Visual Profiler, and there's instructions for how to use them in the README, but I thought I'd kind of go through how they work and what they do, just because the first time you use it, it can kind of seem a little bit overwhelming. So the first thing is you've had to run NVProf before, but you ran it on the command line and it just printed out some stuff, and then you report these numbers. And so there's another way to use NVProf. Let me see if I can find it in here. So maybe you'll have to do this only for MP3 or milestone 3. But let me see if I can find it. Right. So under this profiling section in extras, one way to do it is just to modify your RI build so that you run NVProf and it'll print some results. But the other way to do it is you can generate a file through NVProf that sort of records a bunch of information during the execution of your CUDA code. And furthermore, there's additional modes. So this will sort of capture information that's kind of like a timeline of your code, and it has pretty low overhead. But what you'll really want to do to understand whether your code, your optimizations, the performance implications, if you're trying to understand why the performance changed, you'll need to run NVProf twice. So the first time you do it, you run it to generate a timeline, and I'll show this in a RI file too. But the second time, you pass this additional flag, and you generate a different file that contains a huge amount of really detailed information. And so this first command will take about as long as just running the code itself. This second one will take much, much, much longer. So if your code takes a few seconds to run, it might take 10 minutes instead with this second run. So you have to be a little bit patient when you do it. And I think we've made the RI, eventually if you just like submit a job to RI that does a loop and sleeps or something, eventually RI will kill your job. But I think we've made it long enough that you should be able to go through this analysis process. So if you're finding that your job is getting killed and you're not getting results, maybe we'll have to make it a little longer. But I think it should be long enough. And so then, I don't know if any of you have gone into Rye and downloaded at the end of the execution, Rye will provide you with a link that's really long, and you can download your project directory. So to do this, you'll need to do that because these files will be in your project directory. So you'll have to go and download the files after Rye does. And so I can't run it right now because it takes like 10 minutes to go through. But for example, can I like get rid of this somehow? Maybe it's a little too big. So this is an example Rye file. And so right, this is pretty familiar, right? We copy the code, we do it, and we're trying to run. I'm here. This is for milestone 1, say, but you can do it with any of your code. So you can see I've just modified this so we run the visual profiler, and we run it once to create this timeline file, and we run it a second time. So it's the exact same command, Python milestone 1, except we're running now to create this analysis file. And so if I submit this to Rye, it will just run the code twice and generate these 2 files. And so this is described in the README. And so at the end of the execution, you're going to get some kind of link that looks something like this. Right? It's like some AWS link with a bunch of stuff. And so what you'll have to do is download that. And then you can extract it. So what is this user? Right, and then you'll get this build directory, and that has the state of, yeah. Instead of having to download it?
Otherwise, it's like every time you have to zip it up.
So Rye, so you don't have to do anything to get this zipped up file. Rye does that automatically, and it will print the link for you after the execution. But we don't have any systems set up to authenticate you guys against some other thing where you can SCP. So I know it's a little bit annoying, but you'll have to copy and paste this link, sort of like I did, and download it and extract it. You could modify your Rye file so that it has, a public key, and then you could SCP something somewhere before the end of the execution and zip up the directory if you want. You could do that. But no, we don't have anything built in for that. So you can see that here's that analysis file, right? And here's that timeline file. And so the next step is these files, themselves aren't really readable in any way. So you have to install something called the NVIDIA Visual Profiler. And that's bundled with the CUDA toolkit. So the problem is that if you just have like a Windows laptop or something and you try to download the CUDA toolkit, I haven't actually tried this myself, but I think it will try to, by default, it will try to install CUDA on your laptop. And if your laptop doesn't have an NVIDIA GPU, then it will say that it's not compatible. If you do have an NVIDIA GPU and you have your driver set up the way you like and so on and so forth, I don't really know what it's going to do. There's probably a way to invoke the Windows installer with the same kind of command line and say, oh, I only want certain components. I don't know what it is. You'll have to look online. But we do know how to do it on the EWS machines. So everyone can do this. You don't actually have to physically be in the lab. You can do it remotely, I believe, too. And so instructions to do that are also in the README. Oops. Oh, gosh, what did I do? So, you'll SSH into EWS, and then this little script will download it and install it if you don't want to do anything. But basically, it's going to make a software directory in your home folder. It's going to download the toolkit. It's going to execute the toolkit and say, accept all the user license agreements, blah, blah, blah. Install only the toolkit and install it in software. And so this is a pretty big download. It's a pretty big install, so it takes a little while. But once you do it, you can run the visual profiler by doing this. And so I can also do that because I have it installed on my laptop. And so it might ask you to set some temporary workspace or something. That's totally fine. And let's use this. I don't know how well this is. But then the next step is, this is also described in the README. So you're going to want to import those files that you downloaded. So I'm just going through regenerated them through mvprof, single process. And then the timeline data file, that's that timeline. And the event and metric data files, that's that analysis one. So click on both of those, hit finish, let it think for a second, and then we have this profiler. And so, sorry this is a little zoomed in, but the top part is a timeline of the execution. And so you can see the name of the program that was executed. It has all these different host threads. And so, you know, MXNet is doing all this crazy stuff in the background. So a lot of the timeline is going to be MXNet doing stuff. But you can see it's just a timeline of all these things happening. And if I click on any of these, so for example, here's runtime API. This is CUDA get mem get info. So maybe the system runtime MXNet is checking how much memory is available on the GPU, probably. And you can see, you know, when these things start and stop and how long they take. But what's most interesting to us is we're going to want to go towards the end, and these are where all the kernels are launching. So you can see this is the compute section, and there's all these different kernels. You can see, so this is, you know, MXNet knows that we're running on sort of an older GPU, so it picks a particular kernel implementation and does all these things. But there's all of this information down here about sort of what the kernel's grid size and block size were and how many threads and the occupancy and blah, 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 blah. And so what you're going to want to be able to do is you can find your own, right, the network is doing many things, but your kernel will be in here somewhere. And so you can find it in this timeline and click on it if you want. The other thing you can do...
Wait, how do they identify the kernel?
By name. So when you click on one of these little blocks, if you're not zoomed in enough, it'll show you the name.
Yeah.
But the other way to do it is, maybe I can make this show a little bit more at once. No? Okay, that's fine. Oh well. Is it possible to zoom this out? No. That zoom out button isn't gonna help. So the other thing you can do is it has this sort of guided analysis process. So we can say examine GPU usage. I think when you use on your own laptop, it's going to be a little easier to see everything. But you can see that it has all of these sort of overall suggestions about how the GPU is being used. It's saying that not a lot of kernels are executing at the same time, mem copy is not overlapped with compute, and blah, blah, blah. But really, a lot of this we don't have control over because it's just what MXNet is designed to do for this project. But what you can do is go to examine individual kernels, and then you'll see a list of all the kernels that were executed, and your kernel will be in here somewhere. So this is just the MXNet implementation. So I don't have, you know, my kernel in here, but the operator that you write will be in here somewhere. And if it's executed with different ways, it might be in this list multiple times, right? Because we have different layers with different sizes. But if I care about, you know, maybe my kernel is the slowest kernel, then it will be at the top of the list. And if I care about this kernel, I can click on one and perform analysis. And then we'll start getting some pretty detailed information about this kernel. So this default view is comparing compute and memory bandwidth, but you can do all kinds of stuff. Memory bandwidth analysis. And then it will give you locations where it thinks that there were more accesses than there needed to be to get the particular amount of data, or you can check the global memory access pattern, or how much bandwidth was being limited in each part of the kernel. So for example, we can see this kernel had 1.1 terabytes of aggregate L1 or shared memory bandwidth. So you can sort of make changes to your code and check how all of these different metrics are affected. And so, I mean, there's so much stuff here that I can't go through it all, but you can click through this and kind of check everything that you want. The other thing that I do want to point out, let me see if I can get back to it, is in your kernel, you should be able to look at how much time the code is spending on particular instructions, or how much time the execution is spending on particular lines of code that you've written. Unfortunately, I can't quite show this here, but if you do, you know, under this compute thing, you can hit show instruction profile execution. The problem is all of these built-in MXNet kernels weren't built with the binary can be built with some kinds of debug information so that it knows the mapping of source lines to actual instructions, but your code will be built with that. So you'll be able to go in here, and right now you can see that it's showing how much time is spent on these lines of assembly code. But in your view, you can see how much time is spent on lines of your code. It might prompt you to say, I don't know where the source file that corresponds to this is, and that's because the directory structure on your computer is different than the directory structure where it was compiled. But it should give you an option so you can browse to the source file. So just browse through that project file you downloaded to your operator file, and then it should match everything up. So you can get how much time is being spent in different parts of your code. This is a little bit deceptive sometimes because the way this works is that sort of every so often when the code is executing, the GPU pauses and says, where's my instruction pointer? And then it sort of records, if my instruction pointer was on this line 90% of the time that I randomly checked where the instruction pointer was, then that line is probably taking 90% of the execution time. So this is pretty good, except for the fact that the reason that one line is slow may not be because that line did something wrong necessarily, right? So for example, if I have a line where I'm doing a load from global memory, the reason that load is slow is maybe not necessarily because it's from global memory, but because my access pattern was bad somewhere else and the data didn't get cached. So that's kind of a simple example, but just because a line is slow doesn't mean that A, anything is wrong, and B, some code is just by its nature slower to execute than others, right? So, but you can look at all of this information and try to decide how to understand it and make sense of your optimizations. And so you can go into a lot of detail here in your report if you want. If you just want to kind of look at how different changes affected things like the shared memory bandwidth or the number of cache misses and so on and so forth, without sort of trying to dive in and look at the lines of code or the assembly instructions and so on, that's kind of up to you. But there's a lot of sort of powerful capability in this set of tools for understanding your optimizations. And so we want to see you take advantage of that when you're writing your code. Because people who are really doing actual high-performance GPU work, the devices are getting so sophisticated that you make a change, it affects how the compiler optimizes something. The GPUs have a lot of different capabilities, and it can be very difficult to understand why a small change that you made in your code has a big effect unless you have tools like this.
So Carl, do they still need to compile without the debugging flags for the final run?
So the way we do it is we don't actually, so if you compile something with debug information, sometimes the compiler will not perform certain optimizations in order to preserve some of the debug information. Or some of the debug information actually takes resources to sort of keep track of that could be used to make the execution faster. So on x86, for example, there's a particular kind of pointer that the system likes to keep track of with debug information called the frame pointer. But if you don't care about that, the compiler can use that register for something else during the execution of the code. So what we actually do is we kind of only turn on the bare minimum amount of information that just maps the source lines back to the lines of assembly code, and it doesn't really have a performance impact. So we just leave it on for the whole project. So we don't actually compile in debug mode, because then it just takes forever to run. And plus, then your optimizations don't have sort of a realistic effect.
So when we do the final performance ranking run ourselves, do we compile with that? Or
yeah, so when we do our final run, it's the same as whatever it is that you're doing. So on the same systems. So we won't get exactly the number that you get, but what we do is we'll run it multiple times, and we take the number that makes you look best out of all of those. So typically, our run is faster than the run that you think that you have. But then again, so is everyone else's. So it comes out pretty good. People aren't surprised. So that's how this profiler works. So you can run this on your own laptop, right? You just have to have the files on the machine where you're running it from. I think it should work remotely over EWS with X forwarding. Yeah. So yeah, you can use this. You can take screenshots of this. You can summarize the data and use it in your report. Yeah. So yeah, go to town. It's pretty interesting. And I mean, unfortunately, a lot of the various metrics and things are not extremely well documented. So if you're looking in like great detail about, oh, I don't know, I want to know, what exactly, what's a good one here? Maybe some of these particular stall reasons or something, what exactly it means. It might not really be documented anywhere. You can kind of do some Googling around online. Other people have sometimes asked these questions. You could make some reasonable guesses. But sort of a lot of the basic performance stuff, I mean, like system, shared memory load throughput, it's pretty clear what it is. It's the bandwidth that it's getting from shared memory. But just don't be surprised if you look at some of this and the TAs don't really know exactly what it is, and you don't know exactly what it is, and no one online seems to know or care exactly what it is. That's just kind of the nature of doing this stuff. So that's really what I had to show. Any questions? Yeah.
How detailed do you want us to show it?
Well, I'd like you to be able to explain in your report why so it's something to say, we had this shared memory matrix multiplication implementation. This was the initial performance. We adjusted the block size to be this size because we thought X, this would happen. When we ran this, and so some of the stuff that you think would happen will happen, right? If you adjust this block size, then the number of blocks that you can have, say, executing at the same time, you can kind of know how much that will change. When you adjust the block size, we saw that in this profiler thing, the shared memory bandwidth went up by, the total execution time went down by this, and the shared memory bandwidth went up by this, and correspondingly, the global memory accesses went down by this much. And in our initial implementation, based on this profiling, it seemed like it was limited by global memory bandwidth. And so when our global memory demand went down by 30%, our code sped up by 30%. It all adds up. Something along these lines.
So it's like every single program that has their own GPU, not like one GPU.
So when you're running your code, you'll be the only one running on a GPU at that time. I don't actually know how they're configured, but these GPUs are pretty old. They're Kepler, so it should be pretty repeatable from run to run. But yeah, you're going to be the only one running on a GPU at any particular time.
So you said we have to extract the debugging information, so we might use up some resources. So in the final report, we need to have a separate
So all of the code is all automatically always compiled with this line mapping information. And so you can just leave that in. That's what we'll run it with in the final evaluation. It doesn't really affect the execution time. It makes the binaries a bit bigger, but it doesn't prevent optimizations from happening or anything like that. So you can just leave it in. That's how we'll run it too. Yeah.
Should we be comparing all our optimizations to the baseline, or should we do them kind of this one?
Good question. I think it depends on sort of the nature of the optimization, because you can't fuse the matrix unrolling and the shared memory matrix multiplication kernel together unless you have both of them. So in that case, it probably makes sense to sort of do an incremental effect. But some of them you may be able to compare back to the baseline. So I think it just depends on what you think gives the most insight into why the optimization worked. Yeah, it's tricky. It's not always clear what the right way to do these comparisons is. Good question. Yeah. So actually, the instructions for installing on EWS are for a slightly older release of CUDA. Shouldn't really make a difference, but I'll update them for the newest one. But as written, they should still work. I mean, NVIDIA still has that release of CUDA available. So. Yes.
So I guess no matter how should would make our base code work, and later on it's
Yeah. So right. So the base code performance doesn't really matter so much.
So basically, we can do whatever we want with the base code.
Yeah. So.
It won't be affected by your base.
Right. Well, that's what I was kind of talking about before. The base code, right, for the milestone, we just want to see that it's running on the GPU and it's working. If you're optimizing over the base code and your base code is not very good, it'll be pretty easy to optimize over it. But remember that we're not really trying to grade the optimizations based on how much speed up you got from the optimization per se. We're grading it on your explanation of why you thought the optimization was justified and your evaluation of its impact with these profiling tools and your evaluation of its impact sort of with our model of how we understand GPUs work. Like when I apply this optimization, I expect the number of global memory accesses to change in this way, things like that, and how that all lines up. There is the grade component, which is the performance ranking, where you're compared with everyone else. And so that is just solely based on how fast your final code is. So that is, of course, related to the optimizations that you do and how well you do them. So that's why we don't want to grade the optimization themselves on the performance, because we're already kind of grading the performance a different way. So we just care about you showing an understanding of the optimization, why it might be justified, and your ability to understand in the end how well it worked or not.
So, Carl, are there additional resources about NVProf that
So in the CUDA programming guide, they talk about it some. There are various talks at GTC and things like that. You can find slides online for people discussing sort of some different features of the profiler.
So those are Google findable.
Yeah. But no, there's not like a great description of all the little metrics that can be gathered and what exactly they all mean and things like that, unfortunately.
So, and also, are they familiar with the ranking outcome that we give to them?
I'm not sure. So Andy released a version of the client on the project page that should allow you to run a command to see how fast your code is and compared to all the other teams. So I don't know if anyone's tried that yet. I also don't really know the details
Anyone
of...
tried? Anyone look at the ranking?
Yeah, I'm not too surprised because we haven't even had the
Because we
GPU
haven't-
code
yeah.
milestone yet. But that's there.
I think it's a good idea
Yeah.
to try it soon. Right? Just
Yeah.
to know how you do these things.
And so there's a old, sort of the current version of the client that you're all using. The link is also there. So if you download the new one and it doesn't work for you for some reason, you can go back to the one you're currently using while we fix the new one. Yeah.
Concerning current confusion on Piazza and
Okay.
rubric, do we need a milestone? Do we need an optimization for milestone 3?
No, milestone 3 is just going to be the GPU code. That's the one that's coming up in not too long. And milestone 4 is the one that's in early May.
I told them at least 3.
And 3. Yeah. So sorry the rubric is wrong, but I think the milestone description is maybe right.
Yeah.
Okay. So I'll
update
fix
it.
that.
Yeah.
Yeah. Apologies. We're sort of revising this a little bit as we go. So I was trying to stay on top of the Piazza stuff, but I guess I missed that. More questions?
How about the README stuff? You sent someone sent a message about we have to add a bunch of optimization.
So I posted something on Piazza saying I added a list of optimizations to the README.
Oh, okay.
That's this.
I thought you want us to write a README file.
No.
It's the project README.
Yeah. Yeah. Good.
So would you like to have Carl to repeat any of the steps that he went through? This is the opportunity. We have
Yeah.
a few minutes.
Just to clarify,
Yeah.
I think I just missed it. So we have to run that one command that may take a while.
Mhm.
Those files will be wherever Rye runs on AWS. And then after we download that, is it going to be the whole project folder, or is there a specific file that will get loaded into
Good.
NV?
Great. Okay, good. So I'll go over this again. No, because this is important. So right? When we have our original RAI file, we're typically just running, Python and then the milestone code. So what you need to do is you need to modify that. So instead of running it once, you run it twice. You can see the other one's highlighted here too. And you need to add this first NVProf to capture this timeline. That's the fast one. The second really slow one to capture the detailed information. So
if
that's
they want, they could comment out that last line
Yes.
when they debug. Right?
Yeah.
Because so you want the fast turnaround if you just want to test whether things work.
Right, exactly. Here, so can I go through the flow? And then, okay. So you're going to get these two. RAI is going to run like it normally does. It's just going to be slow. Then at the end, RAI prints URL. So that URL is the zipped up version of your download folder. And so, for example, for me, it was this. And so I download that.
Using a browser.
Yeah, or you can use the browser, or you can, use a command line tool to get it, anything you like. So then that is the project folder. So when I unzip it, you can see that inside it's this build folder, and it contains the entire state of the project. And so inside that folder are going to be these files that were generated by the profiler. So here's the one, and here's the other one. So those are the files that you'll need to go into NVProf and import. So you just kind of click through this. If you have only the timeline file because you're interested in doing some quick turnaround, that's totally fine. You can just put the timeline file up here and click finish.
So if they're running on the EWS machine, they need to put the zip file on the EWS machine.
Yeah, so you have to download that file onto wherever you're running the visualizer from.
So basically, they would do like a SSH kind of thing, and then they would be downloading the file using the HTTPS through that SSH command, right?
Yep, exactly. And then you'll fire this up. You'll add these files into NVProf, and then it will load it and be able to show it for you. And so then you can see the timeline and here, it's all compressed into one view now. So it's kind of interesting. You can see that this is such a simple network that even this inference process is a very small amount of the sort of overall execution time of MXNet. And this is actually a research topic that we're working on in Professor Hu's group, some various techniques to make this a lot faster. Because you can see that this execution is like a half a second maybe, but the whole program takes almost 3 seconds to run, and it's just a lot of this overhead of this framework and initializing the CUDA system and stuff. So, yeah.
So NVProf is a kind of software that we can use to analyze NVProf.
Yeah.
Right, so this tool that I'm looking at is called the Visual Profiler. So that's NVVP, the NVIDIA Visual Profiler. And then the program that I'm using to gather the files for the Visual Profiler is called NVProf. And those are both part of the CUDA toolkit. So this, yeah.
Can we download this kind of software on Windows?
Yeah, so you should be able to. Like I said, though, I don't know what the installation process is like. So you'll download the CUDA toolkit for Windows. So you can go to NVIDIA's website and download that for free. But the problem is I don't know what it will do if you're on a laptop that doesn't have a GPU. You may have to figure out how to...
Not an NVIDIA GPU.
Yeah, not an NVIDIA GPU. You may have to figure out how to bypass the part of it that wants to install the drivers and stuff and just install the toolkit. So on Linux, I know how to do it. It's pretty easy. But I don't know how to... So on Linux, I'm running the installer, and I'm saying only install the toolkit, and here's where I want the toolkit. But I don't know how to do that on Windows. There's a good chance it's possible. I just don't know what it is personally. Never done it. Yeah.
Your suggestion is that we go to the leading system that's provided by the university.
Right. So my suggestion is that from wherever you are, you can go physically, or you can log into the system remotely from wherever you are, and install it onto that system and run it from there.
Yeah, just open the SSH window.
Yeah.
Yeah. Yeah.
Right, exactly. So this little script, well, what this little script does is it creates a directory in your home folder. It downloads the CUDA toolkit installer, it makes it executable, and then it runs it, but doesn't try to install drivers or anything, because EWS machines don't have GPUs. So it just runs the installer, but it only installs the toolkit. And it installs it in a particular location. So in your home directory, instead of like on the system. So it's just for you. And then you can run it like this.
Would they be able to check if it is already installed on the EWS machine?
Well, so the EWS machines don't have CUDA, so I think don't have GPU, so it won't already be installed. But this installs it in your home directory. So you should only have to do this once.
Yeah.
And then the next time when you log in, it should still be there.
Okay.
If it would be installed, it would be installed on the path
Right. So you,
Possibly.
you can check, yeah.
Yeah.
Yeah, or where is, or I don't know. I mean,
The
I can't check
chances
right now,
are
but-
the system administrator didn't really do that in the root. So that's why we always tell people do it once for your home directory, and then you'll be all set. They don't like it when we tell them to install anything.
I haven't logged into EWS in forever. So, I mean, we're essentially done here. You can watch me try this if you want. But
Okay, so if you run into any questions, post on Piazza. If you find any good resources and so on, share on Piazza. Okay, help each other out. Okay, and then this is the best way to do this.
Oh, it looks like I might already have it on here. Okay, maybe not. Oh,
Yeah.
Well, let's see. Yeah, so it doesn't look like it's installed by default, but do I have it in here? I do. You can see that I
Your
tried
home
this.
directory, right? Yeah.
Is it in here?
Okay.
NDPP.
Okay, guys. Very good. Hey, thanks, Carl.
Yeah, no problem. Let's see if it even comes up. Yeah, so there. It works. Magic. Not magic. Lots of
Beautiful.
hard engineering work.
Actually, beautiful.